All right, let's learn a little bit about chords and segment lengths. If you remember from your vocabulary assignment, a chord is a segment with two endpoints on the circle. And there are, as with all of our circles, a lot of theorems that correlate to this. The first of which is the congruent arcs theorem. It says that in the same circle, or two congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So what does that mean? If I look at this example, because I know segment AB, so it gives me this, I'm going to say segment AB from here to here is congruent to CD, and I know that because it gives me congruency marks. So those are congruent segments. Because these segments are congruent, their corresponding arcs are also congruent. So I know that arc AB is congruent to arc CD. Right? That's what the theorem is telling me. And that's pretty handy information to have. I don't actually know the measure of CD or AB, but I could figure it out. If I just give it a value of X, I know these two are congruent. So I could say my two X values plus the 20 degrees to go from A to C plus the 220 degrees to go from B to D will all add up to not enough space. 360 is really what it adds up to. When I simplify that, I end up with 2x is equal to 240? No, that's before 120. Wow, Ms. Palmer can do math. And I can use that to help me figure out that the measure of CD and the measure of AB are 60 degrees. Pretty cool, huh? That opens the door to us doing all sorts of complicated circle work. If I look at this example, I might at first glance say, oh, 80 degrees and 80 degrees, I'm good to go. There we are. But if you don't actually pay attention to the segments that you're given when comparing arcs, you can get into all sorts of trouble. I went ahead and labeled the arcs that are congruent. So if I go from T to R, and I add up the 60 plus the 20, then I get the measure of TR is 80 degrees. I also know that the measure of R to Q is 80 degrees, and the measure from T to P is 80 degrees. All of that I was given or was able to quickly derive. What it's asking me to find is the measure of segment QR, and I would be able to find that if I could figure out whether QR segment was congruent to either of these other two segments. Because if my segments are congruent, then the corresponding arcs are congruent. Well, to figure out, does QR measure 12 units or does it measure 15 units? I have to compare their arcs because my segments will have congruent arcs. So if I look at the measure from P to S of its arc, I learn that arc PS is 100 degrees. I've already calculated the arc TR 80 degrees, and I know that arc RQ is degrees. Therefore, my segments TR and RQ have to also be congruent, and that tells me that the measure of this segment is 12 units. Put your units, Palmer. All right, so that was complicated, but not difficult. I can use that same strategy in example 3. I went ahead and did a little bit of math ahead of time. To find the measure of arc HI, I'm going to add it to the other arcs of the circle, recognizing they should all add up to 360 degrees. And I learned that the measure of arc HI is 78 degrees. If I can find congruent arcs, then I will be able to identify congruent segments. So arc HI at 78 degrees is congruent also to arc GH. That means that their corresponding segments will also be congruent. So segment GH has to be, and you don't need the M if you're using congruency Palmer, segment GH will be congruent to segment HI. And we know that GH measures 9, then I can also say that HI is equal to 9. And that answers that question without too much difficulty. All right, are you ready for another theorem? Sure, let's dive in. The next theorem we're going to talk about works in both directions. It's bidirectional, biconditional, and it says that if one chord is a perpendicular bisector of another chord in a circle, then the first chord has to be a diameter. And you might be saying, Ms. Palmer, in this picture, AD is not a diameter, but it does go through the center. And so if I were to just extend this segment, it would become a diameter. So this theorem is saying that when you have a radius or a diameter that is perpendicular to a perpendicular bisector of another chord in the circle, then the first chord is, yes, then the first chord is a diameter. All right. But because it's a perpendicular bisector, guys, you know that these two segments from C to E is going to be congruent to E to D. So I'm just going to write that. CE is congruent to EB. All right. Conversely, I can go the opposite way. If a diameter is perpendicular to the chord, then the diameter has to bisect the chord. And interestingly enough, it also creates two congruent arcs, right? So this tells me that arc CD is going to be congruent to arc BD. Okay, so that's what that theorem means. We can use that theorem to do some math, even though I just used that picture as a diagram for this theorem. It also applies to this particular problem. So it tells me that AD is perpendicular to BC. That's pretty cool. And because AD could be a diameter, I know that it also bisects segment BC. I know that AE, from A to E, is 7.5, and that the radius of my circle is 8.5. So I want you to remember that AB is 8.5, but so is AD, and so is AC, because all the radii of a circle are congruent. This creates a right triangle. I drew it over here. I can use Pythagorean theorem to find the measure of the segment from A to E. Oh, I lied. This is the segment from E to B. So it's that half of a chord, and that's going to be 4. So if half my chord, or half the chord is 4, that would be to B. If this is 4 units, then we know that E to C is also 4 units, because we already talked about its congruency. If I know that is the case, and we already talked about how all the radii of my circle are the same. So if a segment AB is 8.5 because it's a radius, then segment A to C is also 8.5 because it's a radius, and A to D is going to be 8.5 because it's a radius. And then the last thing I'm asked to find is the measure from E to D, which is this little bitty tiny piece down here. So I know that all of my radii are congruent. AB is equal to AD, which is equal to AD plus E to D. That's the segment addition pilot. I do a little math, and I learn that the measure of ED is 1 unit. There we go, guys. That's how we can use that cool chord perpendicular bisector arc theorem. I use the same logic to solve example 5. In example 5, I went ahead and drew my radii. I know that AB is congruent to AC, which is congruent to AD because all radii are congruent. I know that all the arcs of my circle add up to 360 degrees. So if arc BFC or CFB is 220 degrees, I can find the measure of arc CB by subtracting from 360. And when I do that, I learn that arc CB is 140 degrees. So if arc CB is 140 degrees, then its corresponding central angle is also going to be 140 degrees. I know that because this is a perpendicular, a bisector, because it goes through the diameter, or it is a diameter, goes through the center, then I can use my theorem to tell me that CE is congruent to BD. And I know that the arcs are going to be congruent. So if this whole thing is 140 degrees, then I can surmise that it's split equally into two pieces, making angle BAD a 70-degree angle. And because its arc is also bisected, arc CD is 70 degrees. And we're now, aren't we? One more, actually two more, because I forgot there's a theorem here. This one, going to use that same information. They've already drawn a nice picture for me, and they gave me my my right triangle. Because this goes through the center and is perpendicular, I can conclude a few things. I know that A to this point is congruent to this. I know that these two arcs are going to be congruent. Arc AC is congruent to CB. I know that the radius is 5. And because they gave me this as a 60-degree right angle, I can use my 30, 60, 90 special segment or special relationship to help me figure out what they're asking me here. So I divide by 2 to find the measure of x, which is the side across from my 30-degree angle. And in this case, x is going to be, let's see if I do 2x equals 5, then x equals 2.5. So P is going to measure 2.5 units. I can substitute this value in to my long side, and I know that my long side is going to be 2.5 square root 3 units. And to find the arc measure from A to B, this whole thing, I recognize that if this central angle is, sorry about that, is 60 degrees, its arc is 60 degrees, these are congruent. So together, arc AB is going to measure 120 degrees. All right, last one, I promise. This theorem is wild. This theorem tells me that in the same circle or congruent circles, two chords are congruent if and only if they are the same distance from the center. So I look at this. First, I recognize that they are both perpendicular bisectors. They are perpendicular chords to a diameter, or what could be a diameter. So that means this guy is congruent to this one. And in this chord, I don't use that. In this chord, it's perpendicular, and the rate could be a diameter. So these two parts of the chord are congruent. And what this theorem is telling me is that because my two distances from the center at the perpendicular to the chords, these are the same, that means that all of these segments are going to be exactly the same. That tells me that x is equal to 8. This one's equal to 8. This one's equal to 8 because these two larger ones are equal by my theorem. And if these two together comprise y, then y is going to be equal to 16 units because they all add up. All right, guys, that was a lot of theorems pertaining to chords and segments and such, and that's our lesson for today.